So today we're going to talk about partial fractions. And this is so cool because this is definitely something you're going to use in calculus. In fact, a lot of the stuff that we've done, and I hate to break it to you, but a lot of trig shows up again when you get to calculus. It's different, but you see the trig again. So this is definitely one of those pieces that fits the puzzle for calculus. So for partial fractions, what we're doing is we're taking a large rational equation, so a large fraction that has polynomials for numerator and denominator, and if you can't do the calculus on it because it's just too complicated, well, one of the things that we do to make it easier is break it up into partial fractions, and that's called partial fraction decomposition. So it's absolutely something that you'll see if you go on to calculus. So we're going to write those decomposition factors. We're going to decompose a fraction with distinct linear factors, decompose a fraction with a repeated linear factor, decompose a fraction with an irreducible quadratic factor. We'll talk about what those are when we get there. Decompose a fraction with a repeated irreducible quadratic factor, and apply our knowledge of decomposition of partial functions to graphs. You know, how does all this fit together? And as we go through this, it's one of those things that once you see it, then it starts to gel. So if I'm explaining how this is going to work and you're like, okay, I just can't see that yet, wait until we do one. It'll all come together for you. So partial fraction decomposition. A polynomial with real coefficients might be factored into the product of factors with real coefficients, where each factor is either linear or an irreducible quadratic factor. So this piece here about an irreducible quadratic factor, that's for things like this. Now, why is that an irreducible quadratic factor? Because we can't factor it. You know, we don't know two integers that multiply to 3 and add to 0 so that there's no middle term. So that's an irreducible quadratic factor. And if you ever see one as a trinomial and you're thinking, gosh, I don't know, is this an irreducible quadratic factor? I'm not finding the factors, but does that mean it's not working? Remember that you can always use the discriminant. And if it comes out to be a perfect square, then we know it is factorable. And you should keep looking, and you should keep trying to factor it. You know, whatever you have to do, whether or not you complete the square or whatever, to find those factors. So irreducibles just mean you cannot factor it any further with integers. We can't make that happen. So that's an irreducible quadratic factor. Now, this one says we want to factor x cubed minus 64. It's been a while since you had to factor the difference of two cubes. So we notice that this is x cubed, and hopefully with a little bit of time we would notice that 64 is 4 cubed. And the formula for this involves a little bit of logic where you think, all right, if I've got a cubed minus b cubed, there's 3 of them in there. Obviously, I'm really hopeful that there's at least one a minus b that I could get out of there, and there is. But then you work backwards and you say, all right, if I had to take a times something and get a cubed, that something would be a squared. And if I had to take b times something to get b cubed, well, that something would be b squared. But the problem with that would be we would get a middle term. And we're not supposed to get a middle term. This is just going to be an x and a 4 here that we're looking at for a and b. So what we do is make sure whatever this sign is, we give it the opposite sign for the middle term. And then we realize, well, our a value is x, and our b value is 4. So we can just substitute those in there, and we'll have it factored. So it will be the quantity x minus 4 times the quantity x squared plus 4x plus 16. Now, x minus 4 is a linear factor. It's x to the first. Degree 1 polynomials are linear. And this one, 98% of the time, is not going to be factorable. But you should check. We have to know that it is. Isn't. So we look at this and we think, all right, maybe it's a perfect square trinomial. This is x squared and this is 4 squared. So maybe this works out really super nice. Well, x times 4 is 4x, and when you double it, you don't get 4x. So it's not a perfect squared trinomial. You sit and think for a bit. Do I know two integers? Oh, maybe I should leave that up there in the notes and just put a no it doesn't up here. There, we'll do that. You try two integers that multiply to 16 and add to 4. You spend some time looking for it and you're not finding it. Again, the backup plan is always, hey, it's not showing up. Let me try b squared minus 4ac. So 4 squared minus 4 times 1 times 16. Well, that's going to be negative. I don't even need to know what it is. I just know it's going to be negative, and if it's negative, it's not a perfect square. So this is not going to be factorable. So we have a linear factor. We have the x minus 4. Worked out really nice. But we also have an irreducible quadratic factor. We cannot factor that. So in this section, we are shown that a rational function can be expressed as the sum of rational functions where each denominator is a power of a linear factor or a power of an irreducible quadratic factor. Apparently there was a sound here that's no longer available anymore. It's like ta-da, or something along those lines, So you read that, and that's kind of a head scratcher. What on earth? Rational functions. Okay, so we're going to get fractions, polynomials on the top and the bottom. We're going to break them apart and make them into a sum of other rational functions. So that means we're taking a big fraction and we're breaking it apart into littler fractions. Well, we've never done that. We've taken smaller ones and we've put them together before and, found whatever their sum is. But now we have to work backwards. Well, turns out we have a lot of skills. We've been doing math a long time and we can make this happen. So each fraction in the sum is called a partial fraction. And the sum is a partial fraction decomposition of the original rational function. So our job is to figure out how can we split these up so that they're easier to work with. We have an x to the fourth, a fourth degree polynomial in the numerator, and x to the fifth as our denominator, degree 5 polynomial. Don't want to do calculus on that. It's going to be too difficult. But if we break it apart, we can make it happen. So here it is. We're going to look at it forwards, and then the backwards process is a little bit different. So this says, let's rewrite 3 over x minus 4 plus 2 over x plus 3 as a single rational expression. So I start thinking, they're fancy, but they're still just fractions, and with fractions you have to have a common denominator. So we'd look for the LCD, and we'd realize since everything has to be there and to its highest power, our LCD is going to be the quantity x minus 4 times the quantity x plus 3. So this little bugger needs the x plus 3 on the top and the bottom, and this one needs the x minus 4 on the top and the bottom. So we would go ahead and distribute the 3 in the numerator, but leave that denominator in that factored form. Distribute the 2, again leaving that denominator in factored form. And now we have a common denominator, so we can go ahead and do the addition across the top. So 3x plus 2x is 5x. 9 minus 8 is 1. And only now, at the very end, would we say, hey, anything we can simplify here? But 5x plus 1 is what we have for our linear factor in the top, and that's not matching anything down below. We can't factor 5x plus 1 somehow and make it be x plus 3 or x minus 4. So that's done. So now, what we're going to see today is this. And we take this and break it apart to make it look like that. That's our job. Linear factors, irreducible quadratic factors. Break it apart, make it easier to work with. So, how's all that going to happen? Well, obviously, we're going to want to see what our denominator is in factored form. That's going to be a key. And then what we have to do is think about this process backwards. How are we going to make this happen? So we have this box here to help us out. And it says this section will give us techniques to perform this operation backwards. And we've got partial fraction decomposition of f of x over d of x. And it says the degree of f if it's greater than or equal to the degree of d. So I'm taking a look and I'm saying, oh, well, if that's the case, then we should just divide, and we should see what we have. So use the division algorithm to divide f by d to obtain the quotient and the remainder r. And write it as a quotient plus the remainder over the divisor. We've done that in the past. That's not what today is about. So this is, hey, if you can do the division to make it smaller, do the division. Yeah, we did that in the past. These are, no, we can't divide this. We need to see what's going on. So, number 2, factor your denominator, d of x, into a product of factors of the form. And notice we've got our linear factor here, mx plus n, to some power, if we need it to be, or an irreducible quadratic factor right there. Or ax squared plus bx plus c is not reducible. We cannot factor it any further. Now, for each one of those linear factors, we want to find the number that needs to go on top of that linear factor. So we're going to set them up as some a value. In fact, we're not going to stick with a sub 1, a sub 2. That gets confusing for students. We're going to do a over mx plus n, b over the quantity mx plus n squared, all the way up to whatever letter of the alphabet we need, over mx plus n to whatever the highest power is. So every power of that linear factor has to be represented. Number 4, for each irreducible quadratic factor, the partial fraction composition has to be a little tougher. When we look at this, the denominator was linear. If you subtract 1 degree away from that, you have constants. This is talking about an irreducible quadratic. If you take 2 and subtract 1, you get a 1. This needs to have linear factors in its numerator. And that's as high as we're going to take it. We're not going to do anything with, third power down there, cubics or anything like that. So this will help us break it apart. And again, we're going to use A, B, C, and we'll just keep going with the alphabet instead of using these subscripts in here to make it easier. The partial fraction decomposition of the original rational function is the sum of q of x and the fractions in part 3 and 4. So we want to keep what we had for the initial rational equation, but we have to break it apart to make it workable. And that's what partial fraction decomposition is. So partial fractions are extremely useful in integration and calculus. So we better learn this, but we better take it in steps. So away we go. All right. Write the terms for the partial fraction decomposition of this rational function, but don't solve it. We're not going to try and find it yet. We're just going to break it up. So I look at the denominator, and I see I've got x, and really I want to think of it as x to the first to start with. That's a linear factor. X to the first is another linear factor. X squared plus 1, I think. Can I factor that? No. That's an irreducible quadratic. So now I have to break it apart. And I want to start with 1x as my denominator. But then I realize, hey, when they were looking for common denominators for this, they had to go all the way to x to the third. So there might have been an x to the first as one of the denominators and an x to the third as the other one. Or it could have been an x squared and an x to the third, because remember, we have to take everything to its highest power. So those were all possibilities. Now I can stop at 3 because that was the least common denominator that they could find. Then they obviously had something with an x plus 3 in it. But I only put that one down once because there's no additional powers for that. And then they obviously had something that had an x squared plus 1 in the denominator, because that's how least common denominators work. You have to take everything into its highest power. Now, I want to think about what's going to happen up here on the top. Well, what's going to happen is, this is a linear factor. There's going to be some number a that I have to find. This was also a linear factor because it was x to the first before they had to build it up. So was this before they had to build it up for the least common denominator. Then I look at the next one and I think, well, that's an x to the first. So 1 minus 0 would give me a constant. But that irreducible quadratic over there, 2 minus 1 is 1. So that means I'm going to have a linear term on the top of this. So that would be ex plus f. Now, it could turn out that f is 0, but I do know it has to be a linear factor back there. And so I'd try to figure out how to solve for that. But this is the first step, just setting it up and saying these are the things that I could break this apart into so that everything would be represented. Because like I said, something could come up to be 0 in here, but we won't know that until we solve it. And we're not going to solve this one because we need something a little smaller to start off with. All right. So examples 2 and 3 will show us how those constants, they're using a sub I, but we're just going to use the alphabet A, B, C, D all the way through. We're not going to use the subscripts. So the constants a sub I in part 3 of the partial fraction decomposition procedure can be found. So find the partial fraction decomposition. Yeah, this one is more the style we need to start off with. 5x minus 1 over x squared minus 2x minus 15. So my first job, it said in the box, is to factor that denominator if I can. So I'm looking at it. I'm looking for greatest common monomial factor. Don't see one. Looking for perfect square trinomial. Nope, negative 15 isn't going to do that. But then we know two numbers that multiply to negative 15 and add to negative 2, negative 5 and positive 3. So that step's really big, because that tells me I need something over x minus 5 plus something over x plus 3, because they're both just first powers. And because these are linear here on the bottom, if you take the power of 1 and you subtract, and you're getting 0, well, that means these were constants. All right, we have to find A and B. How are we going to do that? Well, now it's time to think forwards again and say, if I had to do this addition, what would I have to do? But here's what I want you to know. Do you already see that we have this denominator taken care of? We've decided that's what the denominator is going to be because that's what it has to be for this to work out. So we don't have to do any more math with the denominator once we have that factored. We have to figure out what's going to happen up here. So I think, all right, this one has the x minus 5, so I'm going to have to multiply the a by x plus 3. That's what has to happen. And this one has the x plus 3, so I'm going to have to multiply the b by x minus 5. All right. Well, that looks very algebraic. Let's go ahead and distribute. Now that was huge. Here's why that was huge. This tells me that when I'm working with the x terms, ax plus bx, I have to get, because remember, this is our prize right here, 5x. That's the only way this is going to work. And my constants here, 3a minus 5b, well, that has to come out to be negative 1, because that's the only way this is going to work. Now, we've been talking about matrices, and we could certainly set these up as matrices and say, what I really care about is that a plus b equals 5x. I don't need the x's. What I need is 1a and 1b to come out to be 5. And I need 3a minus 5b to come out to be negative 1. But instead, because this is a little 2 by 2, this is going to be easier and faster for us to just do this algebraically, because we can say a plus b equals 5 and 3a minus 5b equals 1. We could use substitution. We could multiply the top one by negative 3 and then add those together. You know, we have a lot of different ways that we can go about this. So I think I'm going to go ahead and use substitution here. I'll subtract b from both sides and substitute that in for a. So we'll get 15 minus 3b minus 5b equals 1. So we'll have 15 minus 8b. Why isn't this working out? Yeah.
Isn't 1 negative?
Oh, thank you. Yep, before I got too far, thank you very much. I wrote negative in my matrix and then I didn't put it on there. Thank you. All right, so we keep going. Negative 8b equals negative 16. Divide by negative 8. And b comes out to a lovely little 2. And then we can go right back up here and do 5 minus 2 is 3. Now, we're almost done, but we didn't write down what those two little fractions are yet. So 3 has to go up here. And 2 has to go up here. And there's our partial fraction decomposition. Now, could we know that we're right? Yeah, because these are supposed to be the exact same expression. If they're the exact same expression, if we punch them into the calculator, it better be the exact same graph. If it's not, we did something wrong. So we could put this one in with parentheses top and bottom because there's more than one term there. And then we'd put this one in. Well, this one would require double parentheses here to get everything to work out right, to see that they're exactly the same graph. So let's just take a second. We won't do this with every one, but the first one should be important. We've got 5x minus 1 parentheses divided by x squared minus 2x minus 15. And then let me move this up a little so we can see our answer. Parentheses 3 divided by parentheses x minus 5 parentheses parentheses plus parentheses 2 divided by parentheses x plus 3 parentheses parentheses. Whew. All right, so now when we hit zoom 6 or graph, we should see one graph go right over the top of the other. And it does. So we broke it apart with the correct A's and B's to make that happen. So like I said, what that means is, well, if they're equivalent expressions, we could do our integration for calculus on either the original or the partial fractions. And if it works out that it's much easier to do the integration with the partial fractions, by golly, that's what we'll do. You know, that's part of math, trying to figure out how you can make it happen. So these should be, there's our little answer. Yeah, because like I said, you could do REF on this little matrix if you wanted to, but it's just faster to do the algebra at this point. And if it's on a test, I don't know. I might take the time to punch it in. If you get really good at this, you're probably just going to go, I don't need to test it. You know, I've got it. Nothing else I need to do. Alrighty, this looks a little fancier. So, decomposing a fraction with a repeated linear factor. So find the partial fraction decomposition of that monster. All right, where should we start? Denominator. Ooh, it's got a greatest common monomial factor this time. That's kind of nice. X squared minus 4x plus 4. Oh, that might be a perfect square trinomial. Let's check that one out. That's x squared. That's 2 squared. If I take x times 2 and double it, do I get 4? That's a perfect square trinomial. So we have an x and then an x minus 2 squared. And it's important that we acknowledge that that's a squared. All right, so we have to break this apart. X to the first has to be a part of it because that's part of our denominator over there. Now, there also could have been just an x minus 2 in one of these, but one of them could have been an x minus 2 squared because we had to get everything there and to its highest power. All right, so far so good. Does everybody see that each of these is only a linear factor? Sometimes that third one makes people think that's quadratic. It's not quadratic, it's a linear factor that's squared. So that makes this easier. Because x to the first, the degree of 1 minus 0, minus 1 would be 0, and we have constants. So there it is. Ben. Okay, a little louder. If this had a power other than 1 in here. So those are our irreducible quadratics, where we just can't get it down to an x to the first. All right, let's build it back up and think about what's going to happen. So our little a is going to need an x minus 2 squared. Our little b is going to need an x and another x minus 2. And our c is just going to need an x. That's kind of nice. So now we have everything represented. We need to know what x minus 2 squared is. The good news is we probably wouldn't even have to think about it. It's right up here. We just wrote it. But you could do x minus 2 times x minus 2, of course. And then let's go ahead and distribute. I don't like that my C kind of looks parentheses-like there. We're make it a little bit more curvy. All right, so now I start thinking. Anything with an x squared has to add up to this negative x squared up here. Anything that just has an x to the first in it is going to have to add to this 2, and then my constants have to be 4. So let's just kind of order that for ourselves. Usually at this point it's a good idea. I'm just counting to make sure I got them all and didn't miss any. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They're all there. So now, if I'm going to use a matrix for this, I'd say this is 1A, 1B, 0C, needs to come out to -1, -4A, -2B, 1C, needs to come out to 2, 4A, 0B, 0C, needs to come out to 4. But look at how we can find A really super quickly and fast. So maybe this is another one where we really don't need to use matrices and the calculator. So A plus B has to come out to -1. -4A minus 2B plus C needs to come out to 2. And 4A equals 4 would be our starter. So we divide both sides by 4. We already have A. Then we'd go back to the first equation, because that one was just A and B, and find that B equals -2. And then we can back substitute one more time, and we'll be able to find C. So -4 plus 4 will be 0, so C equals 2. Almost done. All we have to do is write them. So let's see. A needs to go over X plus B needs to go over X minus 2 plus C over X minus 2 squared. And we've got it. Well, I'm not punching that one in. I don't like embedded parentheses and stuff in the first place, and now we'd have a ton of embedded parentheses as we work with this one here. But we could check it by punching in the original, punching in this one, making sure that they come out to be exactly the same graph, then we're ready to go. Now, let's just say you got to this point and you're like, I just don't want to do the algebra at all. I'm going to do RREF on this and get them. Sure, if it doesn't say you have to do it by hand, go for it, you know. You can turn that process over to the calculator at this point and just use your matrix to get the rest of it. But usually, if we see there's something easy that we could do algebraically, we should do that. Because again, when you punch things into the calculator, you've seen mine, it doesn't always take the negatives I punch in. Sometimes if I hit the 1, it doesn't show up. So that type of thing happens. Better to know your algebra is backing everything up. All right. Now, this exploration here, the first year that we were going to teach this, there are actually 3 different ways to teach partial fraction decomposition. And we thought, well, we'll let everybody see all 3 different ways of doing this. And then we thought, well, that's not fair, because that's just going to confuse everybody. So we went to Mrs. LaRude and said, how do you teach it? How do you want it taught? Here's the 3 different methods. And she said, oh, do it this way. And we were so glad, because that was the first method your book shows. So we're not going to do this. We're not going to do the alternative method. You're not going to need it. We're going to go down here and take just another look at, okay, how does this get more complicated? How do we end up having to do a little bit more with these? So this says use the method of exploration 1, ignore that. We're going to go ahead and do the partial fraction decomposition for this. Usually we'd start with the denominator, but this one's already factored for us. So I want your help this time. We're going to break this apart, and what should we use for the denominators? Oh, good, you got them all. Are any of those irreducible quadratics? Nope. So constants. There we go. Now think forwards. What is the A going to need? X minus 3, the quantity squared. What's the B need? Another x minus 3 and an x plus 2. What does the C need? Yeah, just the x plus 2. All right. So the first thing I would do is expand the x minus 3. So think about multiplying x minus 3 times x minus 3, or even write it down if you have to. And I would expand the x plus 2 times x minus 3. Fix attendance while you guys keep expanding there, and I'll see if we all end up with the same thing. Check in with each other while I go through. So far, everybody's good? Keep going. So that's our system. I don't know about you, but I'd do this one with the calculator. I'd do the matrices on this one. This something obvious isn't jumping out at you immediately to say, hey, I'm going to be able to do this algebraically really quick and easily. 14. Okay, so I put something wrong. Three by 4. Negative 21. There it is. Hit the 4 instead of the 1. That's better. Now the smart bird's going to be angry. And I don't want to scroll back, so 3, 2, negative 1. All right, since I had to go back and fix that one. Somebody read off to me what this would look like, please. What would our partial fraction decomposition answer be? Do we know what we're getting here? This is A, this is B, and this is C. A, B, C, wherever the ones are. Okay. And you weren't even here for the start of this. Did you watch it? Okay. So she's got it. So there it is. Now, some people were either like, well, shouldn't I change this to -1 over? No. With partial fraction decomposition, we want to get everything exactly as it was supposed to be when we did that. And I was thinking this might be when we start to run out of time, huh? All right. Well, we made it pretty far, so hopefully tomorrow the notes won't be that horrible for the rest of this. I don't think I can cut anything out, but we have what? Basically three examples and a fourth one where we just write. So it shouldn't take the whole 50 minutes for a video. But there it is. So partial fraction decomposition with just the one method. And yeah, as you can see, watch yourself when you're punching in those matrices.